later time. Okay.
Good
Yes.
practice.
We're currently being recorded. So yes, I'm going to start the presentation. Um, yeah. So welcome to the L1 design tutorial. Um, my name is Sung Young. You guys know that already. I'm going to skip this slide. So for the outline, we're first going to talk about requirements for the L1 and then how those requirements can drive design choices. And third, talk about how you actually go about designing this stuff, especially in the context of this year's L1 program. So the first step to any engineering project is identifying your requirements. And basically, if you want to know what you want from your L1. What do you want your high power rocket to do? Because this is an L1, the default requirement is that you're able to fly and recover your rocket in a reflyable state. And by reflyable state, it means that um, your rocket may be a little dinged up, it could be a little damaged, but you should basically be able to put another motor in and just put it on the pad and be able to fly it again perfectly. So for instance, if your fin has a itty bitty crack here, that's fine. But if let's say your fin sheared off during flight and let's say your body tube snapped in half, yeah, that's no good. That you're really disqualified. So in addition to this default L1 requirement, you can also add your own personal requirements. You can add additional requirements. For instance, when we did our L1 project over the summer, uh, a requirement that everyone added was that I'm able to launch my L1 rocket at Dodds Park, which is 10 minutes away at Parkland, not Parkland, 10 minutes away in a nearby community college. And I strongly recommend that if you're doing your L1, that you add these requirements as well, just because it makes your launch logistics much, much easier. You just go out and launch instead of having to drive 2 hours out into the middle of a cornfield or something. Another popular requirement is cost because we're college students and we're broke. Um, so yeah, being able to construct your rocket under $40, I think that's very reasonable. By the way, this $40 is before motor costs. Another popular requirement was being able to carry an altimeter, like the peanut altimeter or the Stratologger or the telemetrum if the avionics team lets you borrow it. I don't think they will, but yeah. And there are some other requirements that you could potentially theoretically add, like the last requirements. Theoretically, it's possible, hey, I want my L1 to reach supersonic speeds. But I would highly not recommend that because that way it's going to zoom out of your sight and you'll have a very hard time tracking it down later on. So anyway, requirements. You need to know what you want from your rocket before you start designing your rocket. Does that make sense? Kind of.
Yeah.
Okay. Emma, I'm going to put you on the spot since, well, okay, Thane already started designing their rocket. I don't know where you're at in the design stage, so I'm going to ask you, what do you want from your rocket?
Um, I guess I want it to, I haven't put too much, I was hoping to launch it at the first group launch after break. And I want it to, I don't know, I guess just the other basic L1 requirements, I want it to hit just about the L1 requirement height. Um, and I want to use mostly materials that we have, and I also want to 3D print my nose cone.
Okay. So 3D printing your nose cone and the other requirements, yeah, it can be summarized into this default requirement and then the launch requirement at Dots Park and then the $40 um, budget requirements. Okay, that sounds really good. So I'm just gonna quickly go over the other default requirements. These are just good practices for high power rockets and what you're specifically required for the L1. So for the L1, you must use an H or an I class motor, and then you must have that flight witnessed by 2 L1 certified people or 1 L2 certified person. So that's a requirement. And then here are some other good rules of thumb. I'm just going to fly through them. You need a stability of greater than 1.5 calipers, and then you need a rail exit velocity of greater than 4 times the wind speed at launch day. So for instance, like if you're planning on launching at a, if you want your rocket to be able to launch at a maximum of like 10 miles per hour wind, then you need like, what is it? Around like 60 feet per second of launch rail exit velocity because that is 4 times, um, 10 miles per hour, as you can see from this conversion here. And then some other requirements include eject the parachute no later than 2 seconds after apogee, and then you need to have a landing velocity of less than 24 feet per second. You can refer to this slide later because what I'm trying to get to is this point here. Requirements drive the design. Requirements will drive your design choices. That's the point I wanted to make. Like for instance, Emma, you mentioned that you want to be able to participate in the next group launch, so you want to be able to launch at Dodds Park, and you said that you want to meet basic L1 requirements, which is that you are able to fly and recover your rocket in a reflyable state. So let's see how that requirement can be broken down to like drive your design choices. The first requirement to be able to fly at Dodds Park. It's a pretty big field, but not that big. It's not like those ginormous cornfields that go on and on. It's just a soccer field in the middle of, well, suburban settings. So the Central Illinois Aerospace folks highly recommend that you keep your altitude below 2,000 feet. So that's design choice. That's a limitation to keep in mind. Another thing is that the CIA folks have a waiver to launch motors that are H motors max. So you can't use an I motor. So an L1 certification, you could technically use an I motor, but if you're launching at Dodds Park, you have to certify with an H motor. So that's another limitation put on there. And then let's go over to the second requirements to be able to fly and be recovered in a reflyable state. So for maximizing your chance of recovery, you really want a low and slow ascent. So you don't want to really break the sound barrier. You don't want to go super fast. You want to go well, low and slow. And that makes it really easy to keep track of the rocket. And that intuitively means like you're increasing your drag. And that means basically these four things or more. But these are the design choices I went with my L1 rocket. So a blunt nose cone to increase that drag, the front of a rocket, and a 4-inch diameter body tube. Now I could have very like easily used a 3-inch body tube, but by using a 4-inch body tube, you're just increasing that cross-sectional area, so you have more air to push out of the way, so more drag. Large fins, again, same principle. You have more surface for the air to experience like friction and shear forces. And then lastly, I chose a not a very particularly powerful H motor, so H143. So H class is also kind of a range. So every motor class is a range, and at the upper end of the range, you get like really a lot more impulse than the lower end of the range. So that's another thing to keep in mind. If you're choosing the certifiers don't care as long as you have that like the correct letter in the name of your motor. So within that range, you have freedom as to like which motor you can choose, what amount of impulse you're going to give your rocket. So those are the design choices I kind of came to. And then last thing I wanted to do was um last thing to keep in mind is you need to be robust against landing damage. So I guess like the two greatest stresses that a rocket will experience is, well, during ascent, the aerodynamic forces. But if you're doing your L1, you're probably not going to like reach supersonic speeds. So your aerodynamic forces are going to be kind of low. Um, and I think the majority of like damage comes from like landing itself, especially like hard landing. If your rocket accidentally drifts off the soft grassy field and if you accidentally land on like a hard roof or a concrete parking lot. So yeah, that's something I kept in mind. Like you need to be robust against landing damage. And what part of the rocket lands first? Well, it's typically the fins. So I'm gonna show my like L1 rocket design in the next slide. You will see that there are no sharp edges at the bottom of the booster. So don't do what like cartoon rockets do and have like really sharp sticky fins. Yeah, don't do that. That's something I try to avoid. So that your fin's not damaged and the certifiers will see that, oh, this rocket is in a reflyable state. So yeah, keeping all that in mind, this is my L1 rocket. As I talked about, I have a rounded nose cone, I have large fins, and you can see that yeah, there is no sharp like pointy like edges that are gonna like hit the ground and potentially snap off. It's very like obtuse, this angle. Any questions, comments at this point? Okay, in that case, I'll move on. Um, so, so to briefly go over like an unmodded L1 rocket, like a vanilla rocket that these are the components that are going to be included. I'm not going to list them off, but here's how they're broken down into. Um, you actually go on Open Rocket and start designing it. You have the nose cone in the front, and then you have the body tube. And in this rocket design, your nose cone is the part that pops off and deploys the parachute and all that. And whatever payload you might want to carry, you will put inside your nose cone in this design. And yeah, you have all your standard components. So you have nose cone, you have body tube, you have shock cord, parachute, and motor mount tube that holds the motor, and you have two centering rings to center the motor mount tube in place, and you have well your fittings at the bottom of the rocket. So that's like a perfectly fine like L1 rocket design. Um, but yeah, but there are other like potential variations you can put to this design. I don't know. So I want to kind of like open it up and see what you guys have in mind. I don't know, what are some potential ways this design could be varied?
Well, I noticed that you had like more of like a rounded nose cone.
Okay, it's like a different nose cone geometry.
Yeah. Same with like
You
fins.
you can change how high the stuff that you put inside the your payload in the rocket is, so that it could like change the center of gravity.
Yeah, it's true. It's true. You can change like how your payload is positioned inside the nose cone. Um, Another thing you could try and kind of think about is like adding another section to the rocket. Like so this design has well, it separates the nose cone and it's just one body tube after that. After the nose cone, there's one body tube. Another variation you could do is by adding a coupler and you can add a second body tube. So you have a nose cone here and then an upper body tube, a coupler to join that upper body tube with the booster. And if you like, for instance, go with this design, you can add like bigger payloads since you have all of this upper body tube that you can fill up with payload. Um, I know this is kind of like this might seem like a very trivial thing, but the idea I wanted to drive here was that yeah, this vanilla design that's all great, but you can customize it to whatever degree you want. Yeah, so I guess that comes to this slide, customize. So you can start with the vanilla rocket design, but you can like customize it however you want. And your requirements should really drive this process. Like, what do you want from your rocket should really drive this process. And then another factor that will drive these decisions is thinking about what components are available. Like Emma said, you should. I highly recommend that everyone first try to utilize the components that are available in Opal, and that by doing so, this is by far the cheapest option for getting your L1 built. Um, like it's gonna cost like $30 to $40 per rocket for you guys to be able to build it. And this is excluding the motor cost. And here's a link to the current inventory of the things that are available in Opal. Anyway, this is like a pretty sprawling spreadsheet. So I have a slide in the next slide, I have a very like brief summary of all the parts that are available. So the three parts that we have most are 3-inch mailing tubes, 1.5-inch mailing tubes, and then centering rings. So I highly recommend that if you're building your one from scratch, that you utilize these three components. So this 3-inch milling tube you can utilize as the body tube, and this milling tube you can utilize as the motor mount tube, and the centering ring, well, you can use to join this motor mount tube and the body tube. And you have, and here are all the inner and outer diameters for all of these components, and the notes for how you can model these components in Open. And then kind of going back to the last slide, if there's like a part that you really, really want and it's not available, so you can request these components on the order sheet, and then we'll group order it just so we can drive down shipping costs. But that option is but that ordering sheet that's not active yet, that's not available yet. I will get that online if there's like a lot of demand for it, but yeah, it's not available. So yeah, questions, comments at this point?
No, no.
I just have some
Good
like
refresher.
questions about like why did you choose like a rounded nose cone in your like L1 over like a pointed one?
Um, well, okay, this is being recorded, so I'm gonna give you like the very so I'm gonna give you a version of this. So I wanted to maximize strike. And what better shape is there than like a really, really blunt nose cone, right? And look how low the apogee is. I think this was pretty close to what I ended up getting in real life. And if you go this low, you can see the rocket like arcing over in the whole trip, which I think is more impressive than just seeing your rocket disappear into the clouds and like you don't see it, and then people start shouting, there it is," and you see the rocket coming. I wanted to be able to see my rocket the entire time. That's the reason I'm gonna give in this recording.
Suspicious, but okay.
Yeah.
Um, I also I just had like questions about like which motor am I looking at for Open Rocket? Because
Oh,
I was trying to.
Sure. So, I didn't include it in this slide because I thought it would be like too much information at once. But um, so there are like two types of motors. There are like reloadable motors and there are single-use motors. Single-use motors, you just plug it into the mo rocket, and after it's burned out, you throw away the whole thing. When the reloadable types, you have a casing, and then the part that goes on screws into the casing itself, and that tends to be a bit cheaper in the long run since the casing is reusable. It's just the inner parts that you swap in and out. Um, so with that thinking in mind, we purchased like a bunch of like 38mm Cicerone motor casings. So long story short, as long as it has like the same dimensions, same diameter and length as the H143, um, Cicerone H143 motor in Open Rocket, then it should be compatible with all the casings we have available in Open. And that diameter and length is what is it? So yeah, as long as it is 38mm in diameter and 186mm in length and made by Cicerone technology, you should be good in terms of using that motor. Here it is.
Okay. What about
So,
like the altimeter we're using? Can we like model that in Open Rocket, or like how do we like make sure to account for like designing like a place to put the altimeter in our L1s?
so let's see. Like the best thing we can do in Open Rocket is just modeling things as mass components, right? Um, like uh, let's see, like Stratologers, I believe, is like around like 10 grams, so like 12 grams. That's pretty much it. In Open Rocket, it's just a blob of mass. You don't really get to specify if it's like this. It's not a CAD model at all. So Open Rocket does have its limitations in that sense. Um,
What
Yeah.
about just like planning for it in general? Like, is like, do I just get like a board and kind of tape it on there? Like,
Oh, I mean, I was like, how do I mount it inside the rocket?
yeah, like how do I like plan for that?
Yeah, sure. Let's see if this thing, I don't think will work that well. So I think a very popular avionics board design is one where I have my stylus ready. So let's see, it's one where you have a tubular section. Um, so Emma, like, where do you want to put your altimeter? Do you want to put it inside the nose cone or the coupler, or how do you want to go about it?
Um, I haven't really gotten that far yet, but maybe probably and like the coupler.
Okay, so if it's like a coupler, then it's okay. Um,
But if you like recommend like either or, I haven't really gotten that far yet.
well, you can definitely like customize things, but like a very default, very like common avionics bay design is one where you have let's see, you put your avionics in a coupler, so the purple part is the coupler, and you have two sets of bulkheads or a bulkhead with a whip, which you can see here, the whip design here on either end, and you put threaded rods through either of them. You have two threaded rods going through. And on top of that, you put some kind of a board, like a flat piece of plywood or cardboard, even if you have a very light load. And on top of that board, you can mount whatever electronics you want on there. That's like a very common design. But honestly, like heck, you were in AV structures last year. I'm sure you can come up with something that will work. That's like really good. And yeah,
Yeah, I mean, I'm not too worried about the actual mounting. I'm more worried about like what electronics like so I just like I need to put on there and like stuff. So I just need like so does the alt I know this might be like a dumb question, but like so does the altimeter just like go like directly to like the parachute or like I don't know. Like I'm a bit confused on like
are
I
you
don't know.
talking about recovery sequence? How does that work for these?
Yeah.
Okay. Oh,
Or is the altimeter just to like for like the L1 people to determine how high you want?
well, first of all, there is no height requirements in the L1 certification. Like,
Oh.
yeah, the certifiers don't care as long as they see it go up and then come down safely. They don't care how high it goes. Like, you could go up to like 5,000 feet or 1,000 feet. They don't care. Um, so there's no altitude requirement in that sense. So actually, you don't even need to put an altimeter, unless you really want to measure like how high a rocket went. Like Gotham didn't put an altimeter in his rocket; he just flew it without anything.
Okay.
But as for like how that parachute comes out, do you remember like A100?
Yeah, so it's just like yeah, I got a little confused on like why we needed an altimeter. So
I don't need
I
one. Yeah,
I yeah, I understand like it's just like the friction or like not the friction, just like the kind of just pops out when it apogees.
yeah. You got like small explosive charge at the end of the motor, and
Okay.
pops out everything. Yeah, for H class motors, yeah, all of them will come with the ejection charge. As you go into like higher and higher motors, like the one Space Shot is using, they don't have an ejection charge, I don't think. But yeah.
Wait, hold on. Wait. So how does the ejection charge work?
So it's motor model rocket. Can I spell model? Yes, probably. not shopping, sorry. I was hoping to go to images. There it is. So so first, like the propellant burns the green part, and then you start generating thrust. And when the propellant runs out, the rocket's still going up, and you start burning into the delay charge. And after you burn through the delay charge, um, then the ejection charge is triggered. Like that's just a lot of like black
Okay.
powder explosives, and that just pressurizes whatever's in front of it and just blows everything out.
Oh, interesting.
Timed bomb that you put inside a rocket.
Nice.
It's nice.
So the Stratologers will be like available for like the L1s though? Or no?
I think so. That's kind of I between me and I guess Peter to talk about, but I think so. I mean, they're like four, like six. There are like there's like multiple Stratologers floating around, so I can't see why they wouldn't let us use a couple.
Okay.
But like again, you don't have to. It's not a requirement for L1. And also you don't have to use a Stratologger. So there's also an altimeter called Peanut altimeter that we have in stock. Um, let's see if we have it. Is that the manual? Yes, this is the manual. I don't want a manual. I want an image. I'm a visual learner. There it is. So it's this cute little altimeter. Um, let's see. It's yeah, for context, this tube's diameter is 24 millimeters, so it's about an inch in diameter. And yeah, it's this little itty bitty little thing. And the great thing about this altimeter is that it has an onboard battery, so all you need to do is like turn it on and then just mount it. You don't need to worry about 9-volt batteries or anything. So if you're just looking to like put an altimeter in there just to see just so you know how high the rocket went, I recommend using a peanut altimeter that we have. We have like 5 of them. Um, like, one thing the peanuts can't do is ejection charges, and this is where the strata water comes in. But if you're not doing ejection charges, then you don't need to use a strata water.
Yeah, so just with like the regular motor, like like a peanut altimeter is all you really need, right?
Say that again.
Just with like the motor that has like the built-in injection charges, like the peanut altimeter. It's like all you need.
Yeah, if you have a motor with built-in ejection charges, then yeah, peanut altimeter is yeah all
Okay.
you would. Yeah.
And I noticed there's also like different like screw holes on the peanut altimeter. Do you know which ones we have?
Ooh,
There's like the diagonal ones and there's like the right across ones.
yeah, I think we have the right across from ones. So sorry, do you have the diagonal ones? So the one I'm showing right now, I think we have
Okay.
those. Are you trying to like laser laser print or laser cut all the holes or something?
I don't know, but I feel like that's a thing to know before I start designing.
Well, if you're just mounting this, then literally just get a piece of cardboard, poke some holes in it, it was like they're mounted. That's
Yeah,
kind of what I
fair.
did like the day before launch. Um, yeah, but yeah, great questions, Emma. Keep them coming if you have more.
Um, then you have all like the parachute stuff. Oh,
Sorry.
bulkheads. Like well, I feel like I had a question earlier, but so we can just use like plywood lying around or something.
Yeah, we have a bit of lying around. So all one most of them are 1/8 inch, so that's the one we have in most abundance.
For the fins, do you recommend using like is that like a thing that for just like plywood or like
I used plywood for my L1 and everyone else did, and they all worked. Except for
Okay.
the ones that crashed, but they crashed, so. Yeah, 1/8 inch plywood. We use that for everything, like bulkheads, centering rings, everything. We just laser cut them all.
Okay.
If that's the last question, I'm gonna end this recording here. So I know how to do that, so I know how to end the recording. Not a sec. Just being a boob right now.